Wow! Not so fast.
Am I in a multiverse? I've got to check with Cindy.
Okay, I think you've accidentally summoned a riddle from the fourth dimension.
Let's dive into the challenge using algebra, as usual. Here's the final masterpiece we're aiming for. 5CO2 plus 5NH4 plus O2, right arrow, C5H7O2N plus 4NO2 minus plus 2H2O plus 9H plus. Looks intimidating? Don't worry, we're going to tame this beast together. Let's break it down. Start by giving each compound a coefficient. We'll set D equal to 1 because we're balancing for 1 mole of biomass. That's our anchor. Now we write balance equations for each element and charge. Charge? Yes, charge. You need to balance charge if an equation has ionic species. Let's plug in A equals 5. From B equals 1 plus E and G equals B plus E, we get this. Now substitute into the hydrogen balance. Crunch the numbers. Now we've got this. Let's tackle oxygen. Substitute E equals F plus 2. We need C to be a whole number. What's the smallest even F that works? Let's try F equal to 2. All whole numbers. Here it is, beautifully balanced. Let's double check.
Ta-da!
Everything checks out. Balancing chemical equations doesn't have to be scary. It's just a puzzle waiting to be solved.
Wait a sec. I've seen other versions of this equation that still balance. What's going on?
Great question. At first, it feels like there should only ever be one right balanced chemical equation, but in reality, multiple valid balanced equations can exist in certain circumstances. Here's why. 1. Underdetermined system of equations. Balancing is basically solving a system of linear equations, one for each element and charge. Sometimes the number of unknown coefficients is larger than the number of independent balance conditions. That means the system has more than one solution. In our case, there's freedom in how many NO2 minus, H2O, and H plus appear, as long as the balances close. That's why we found a small solution with modest coefficients and other large solutions with completely different numbers, not just a scaled version. 2. Multiple reaction pathways or conventions. Pathways, some species can be produced in different proportions depending on whether the reaction represents aerobic versus anaerobic respiration, complete versus partial oxidation, etc. Conventions In biochemistry or environmental engineering, people often choose coefficients to match experimental stoichiometry, empirical yield data, or to normalize something. For example, per mole of biomass formed or per mole of substrate consumed. For example, our large solution represents a simplified model for the biological process of bacterial digestion or nitrification, particularly in the context of wastewater treatment. In this process, nitrifying bacteria consume carbon dioxide and ammonium ions and use oxygen as an electron acceptor to grow and produce new bacterial biomass. C5H7O2N is a widely accepted empirical formula for bacterial tissue or biomass. So, multiple valid balanced equations are possible whenever the balance equations don't fully constrain the system. Chemists or engineers usually pick the form that's most meaningful for the context: minimal integers normalized to a substrate or product, or based on experimental yield. Now, let's analyze our reaction algebraically with linear algebra to see why more than one balanced form is possible. 1. General form. We want coefficients A, B, C, D, E, F, G in the general form of the equation. 2. Balance equations. Set up equations for each element and charge.
For carbon, we get A equals 5D. For nitrogen, we get B equals D plus E. For hydrogen, we get 4B equals 7D plus 2F plus G. For oxygen, we get 2A plus 2C equals 2D plus 2E plus F.
Charge. B equals minus E plus G. That's 5 equations. Number of unknowns. Unknowns A, B, C, D, E, F, G, so 7 unknowns. Equations, 5 independent equations. So 7 minus 5 equals 2 degrees of freedom. This means the solution space is not a single line, scaling of one answer, but a plane. Multiple independent solutions exist. 4. Express general solution. Let's choose D, that is biomass, and F, that is the number of H2O, as free parameters. Then, from C, A equals 5D, from N, B equals D plus E, from charge, G equals B plus E equals D plus 2E, from H, 4B equals 7D plus 2F plus G, from O, 2A plus 2C equals 2D plus 2E plus F. Now work it through. Step 1. Use H-balance. 4 times D plus E equals 7D plus 2F plus D plus 2E, which simplifies to E equals 2D plus F. Then B equals D plus E equals 3D plus F, and G equals D plus 2E equals D plus 4D plus 2F equals 5D plus 2F. Step 2. Use O balance. 2 times 5D plus 2C equals 2D plus 2 times 2D plus F. Thus, C equals minus 2D plus 3 halves times F. 5. General solution. So the coefficients are A equals 5D, B equals 3D plus F, C equals minus 2D plus 3 halves times F, D equals D, free, E equals 2D plus F, F equals F, free, G equals 5D plus 2F. This shows 2 degrees of freedom, namely free choice of D and F. 6. Particular solutions. Small solution, the previous one, choose D equals 1, F equals 2. Then A equals 5, B equals 5, C equals 1, E equals 4, and G equals 9. Our large solution, choose D equals 1, F equals 52. Then A equals 5, B equals 55, C equals 76, E equals 54, and G equals 109. Both are valid because they're just different points on that 2D solution plane. Let me plot the solution space
A, B, C, D, E, F,
G as a 2D lattice of integer points so you can see how many alternative balances exist. Summary of what you're seeing. I treated D, biomass, and F, number of H2O, as the two free integers and searched D equals 1 to 6 f equals 0 to 60. I kept only solutions where every stoichiometric coefficient is a non-negative integer. So c equals negative 4d plus 3f over 2 must be a non-negative integer. The scatter plot shows allowed integer pairs d and f. Each vertical column corresponds to a fixed d. The many valid f values show the 2D family of solutions.
Can you show me some more chemical equations that don't have just one way to balance them?
Sure thing. There are definitely chemical reactions where the atom balance equations don't constrain everything uniquely. Like I said, this happens when the reaction as written is underdetermined. That is, more unknown coefficients than independent conservation equations. Let me give you some simple examples. 1. Nitrogen oxides from the reaction of N2 and O2. N2 plus O2 gives NO and NO2. Unknowns, 4. Independent balances, 2. NO. Degrees of freedom, 2. Here, infinitely many integer balanced equations exist. Different mixes of NO and NO2 are consistent. 2. Partial oxidation of methane. CH4 and O2 combine to make CO, CO2, H2O, and H2. Unknowns, 6. Independent balances, 3. CHO. Degrees of freedom, 3. Depending on how much CO versus CO2 and whether H2 appears, many balanced forms are possible. Now you've seen how it all clicks. Wasn't that fun? Sometimes the most puzzling problems turn out to be the most satisfying once you crack them. Keep questioning, keep exploring, and don't be afraid to get a little stuck. That's where the real learning happens. You've got this.